Thank you very much. I'm very happy to be here today. I want to start by asking you to picture yourself at a zoo. We're in the reptile house, and there's a plate of glass behind which there's a cobra. Tell me, is there a hazard there? Well, yes, it's a very toxic animal. Is there a possibility for exposure? Probably not, because we'd have to assume that that cobra could leap through the glass and get to me. So is there a risk? Not very much. Now somebody drops a tarantula into that enclosure, and there's a little opening at the bottom. Well, is there a hazard? Yeah, that tarantula, I'd rather not be bit. Is there an exposure? At that point, I'd really like to know how big that opening is at the bottom, how enterprising that tarantula is, and how little it is, could it squish into that little opening and get to me? So is there a risk? Possibly, because there's a hazard and there's a possibility for exposure. Now, what if we took a fluffy little baby bunny and put it into the enclosure, and to get away from those horrible animals, it takes a big leap and it jumps over the glass? Was there a hazard? Not very much. We're not very worried about the bunny. Was there an exposure? Absolutely. It landed in my lap. But was there a risk? Again, not very much. Why? Exposure, but not very much hazard. Those are the concepts that we have to understand when we talk about setting specifications for any contaminant. Pretty simple, but can be very misunderstood and misused. So how do I define those terms? How did I know when I had a risk and when I didn't, and what was that risk? Well, hazard is a type of toxicity caused by a chemical. The manifestation of that hazard depends on the route, the duration, the frequency of exposure. The risk is the likelihood that that toxic property will be produced in the population of individuals under their actual conditions of exposure. And the way we quantitate that is we look at dose responses of chemicals. We understand how much produces what kinds of effects and where those exposures don't produce those adverse effects anymore. Safety is a very difficult term. It's probably the one that consumers use the most. Am I safe? But safety is not absolute. Safety is defined as little or no harm resulting from a chemical, again, under a set of exposure conditions. It's not an absolute absence of risk. It's the inverse of risk. So when we're setting specifications for contaminants, what we're trying to do is control risk, not eliminate hazard. The absolute absence of risk can only be proved if we're certain that the exposure doesn't exist. So if we see a sentence, I can't find it, so it must be safe, there's a fundamental flaw in that rationale, and that is that it depends upon, or the absence of detection of a chemical depends upon the analytical capability to detect it, the presence of the chemical and the magnitude of the health risk that it poses. So when we have to link, is it safe or is it there, we have to link this no residue or an acceptable residue not only to our understanding of the hazard and the exposure, but we have to link it to a method of analysis. So we're constrained by the limit at which we can detect something. So all of these factors have to go into setting a specification. Specifications for fish oils, there are many specifications that we set for many reasons, to assure quality, to assure efficacies that we're trying to establish, to control potential hazards so that we can control risks if we understand what the exposure would be. And we're looking at physical chemical properties, fatty acid compositions, and contaminants through environmental sources. Physical and chemical properties like appearance, odor, taste, density, chemical characterization of fatty acid composition. We're of course very interested in how much EPA and DHA is in there. And then we have environmental contaminants. We have contaminants that come in through sourcing. We have things like pesticides, heavy metals, PCBs. And there are biological contaminants that come in from the environment, contamination from things like yeast or mold or aerobic plate count. We need to control all of these. So how do we set a spec, and how do we know where that spec should be? And how do we know that we've controlled the risk? Well, we're going to use this as a case in point or an example of how to set a spec, or what questions we should ask ourselves when we're looking at that specification to make sure it's appropriate and it protects the food grade status of that product. So in the Prop 65 lawsuit, it was said that PCBs are known by the state of California to cause cancer and reproductive effects, and then ingestion of certain fish oil dietary supplement products causes California residents to be exposed to PCBs, one of the environmental contaminants. Well, let's ask ourselves, what should be the health-based criteria for establishing a specification for PCB contaminants in fish oil? PCBs are part of a class of compounds that are called dioxin-like compounds. Dioxins are related chlorinated compounds. They have similar chemical structures, and they include PCBs as well as PCDDs and PCDFs. And all of the individual components are congeners. The dioxin-like activity is based on a congener's ability to bind to a specific receptor in the body. It's the AH receptor, and it's ubiquitous, it's very powerful, it regulates many enzymes and other proteins. And if a response is evoked, then it is said to have dioxin-like toxicity. 12 of 209 PCB congeners have dioxin-like activity. The others may also have toxicity, but they are not dioxin-like activity. They manifest toxicity through other mechanisms of action. This is what a PCB looks like. Chlorines hang off those meta and ortho and para positions and accounts for all the different congeners. So the most toxic and the best studied of all these is 2378 TCDD. The remaining 28 compounds, dioxin-like compounds, have been assigned toxicity values relative to this compound. And so this is one way, if we're trying to identify, or we're trying to look at the hazard component of a risk assessment so that we can establish what the risk is and where to set that specification, one thing we can look at is what is the dioxin-like activity. And so there are relative toxicity values that have been assigned to PCB congeners, and these are called toxicity equivalence factors. WHO has established a scheme of toxicity equivalent factors. However, dioxin-like compounds exist in nature as mixtures. There's many, many of these congeners. And because many of these differ in their toxic potential, the way that we estimate the overall toxicity or the hazard, again, is to look at the concentration of each congener that's in there. We multiply it by the toxicity equivalent factor to produce what they call a TCDD, toxilant equivalent concentration. So we're looking and we add them all together. And this tells us, in relation to the most toxic of the dioxin-like materials, 2378 TCDD, how toxic was this? Because I'm not mathematically inclined, this will be the only equation you'll see. So this just tells you in a mathematical equation what I just said, which is basically we calculate a toxicity equivalence factor by multiplying each one of the congeners by its toxic equivalent factor, which is in relation to 2378 TCDD, how toxic is it? And we add them all up, and then we determine what our TEQ is. Now there's TEFs, again, for only 12 of the PCB congeners. And the mass of PCBs is, the bulk of them are non-dioxin-like toxicities. There are other toxicities, not as well known, mechanism is not as well studied as those for the dioxin-like PCBs. These are the TEFs. And I know the print's very small. On the far right column is the WHO 2005 TEFs. And if you can't see it, what it tells you is that the toxicity equivalent factors for PCBs are very, very small. In relation to our reference compound, 2378 TCDD, these are very, very small. In terms of, instead of 1, we have numbers 0.0003 and 0.001. So they're much, much smaller, have much less toxicity than our reference compound. Well, why are we worried about PCBs? Lots known about the toxicology. many from animal models. Extrapolation to humans, in some cases, is tenuous. In some cases, there's more evidence. The only overt toxicity from exposure really is chloracne. But in the literature, we can see potential for reproductive and developmental effects, and that's been shown in some humans that have been exposed to massive quantities through very PCB-contaminated fish. There is some potential for mimicking of endocrine effects. There is liver damage that has been shown in PCB-exposed animals. And on the basis of high-dose animal studies, PCBs are considered to be a probable human carcinogen. EPA has classified it as group B2, probable human carcinogen. So with all of those toxicities, one of the ones that I want to point to, because when we're thinking of toxicity and we're thinking of controlling these effects, we need to look at relative toxicities and perception of toxicities, because endocrine disrupting chemicals, that's a really nasty term, isn't it? Endocrine disrupting, not endocrine mimicking, not endocrine-like, endocrine disrupting. It doesn't even sound good. And these are man-made or naturally occurring compounds that can interfere with hormones. And of course, as we learned a lot about hormones today, profound effects can occur. So endocrine disrupting chemicals are a class of compounds that may interfere with normal communication between hormone messengers and receptors. And very, very importantly, why we worry about it is because toxic effects can be seen immediately, but it's possible that changes can occur that can cause toxicity that might not be expressed for years. And that's very worrisome. So endocrine disrupting chemicals, there's a lot of them out there. Just to put this in perspective, probably the biggest source of endocrine disrupting chemicals is in this room. It's every one of us. And any woman in here who's ever taken a birth control pill, 90% of that gets peed out. And you know what? Wastewater treatment doesn't get rid of that. So we are actually a very bad source of endocrine disrupting chemicals. It comes from us, it comes from consumers, it comes from agriculture, it comes from PCBs. So there's a lot of different potential sources. Everybody, the press likes to pick on industrial chemicals, but we have to remember that we're surrounded by natural sources, soy plants, we're surrounded by us, we're surrounded by a lot of sources of these things. Some are much more potent than others. However, why is there concern? Again, because there is indication from some studies that harmful effects can be manifested in reproduction, growth, development. We've seen this in some wildlife. We've seen some human reproductive disorders as a result of endocrine disruption. And we've seen some adverse effects from environmental chemicals known to act on the endocrine system in experimental animals. And so this is an endpoint that has a high outrage factor. There's a perceived susceptibility in a sensitive subpopulation. My God, children could be exposed. This is, not to make light of this, this has a very high outrage factor for consumers. And so what happens is we get into the situation where, when setting a spec for this, we begin to think, oh, we should apply the precautionary principle. Well, what's the precautionary principle? I'll put a definition here. When human activities may lead to morally unacceptable harm that is scientifically plausible but uncertain, action shall be taken to avoid or diminish the harm. Well, the key word here is uncertainty, because uncertainty about how to assess the risk underlies the precautionary principle approach. And instead of asking the question, how much risk is allowable, when we apply a precautionary principle to set a specification, what we're asking is, how much hazard is possible? And as we saw at the very beginning, if I have a plate glass in front of me, I don't care if a cobra's on the other side. It can be as hazardous as it wants to be. It's a combination of the hazard and the exposure and a true assessment of the risk based on the toxicity and dose response. That's what we really need to think about. There are ways to look at endocrine disruptors, and EPA has many more details than this, endocrine disruptor screening program, testing that we can do to really look at these kinds of chemicals and how to evaluate them and how to get at the answer to these questions that we would ask. So we've talked a little about the hazard. Let's just talk about the exposure end, or part of the exposure end, and that is, well, we really have to know how much is in there. And we have tools to do that, and there are ways to analyze and measure how many PCBs are in the product. There are non-specific methods. Non-specific methods, while cheap and easy, are generally have very low sensitivity. And what we need to do is to make sure that we understand how much should be in there so that the hazard and the exposure results in an acceptable risk, and we have to match our analytical capability to that assessment of a health-based standard. Specific methods, of course, have a lower limit of a much better sensitivity, and methods include chromatography, mass spectrometry, EPA methods are commonly used, and they have a very good sensitivity. We can get down to very low levels. These are limits of detection for a commonly used EPA method. The matrix in which we're measuring it has a great deal to do with the limit of sensitivity, of course, because in water, you can see we can get down into parts per trillion, whereas in something like tissue, we're at parts per billion. So the matrix in fish oil would be a very complicated matrix. We have much less ability to get down very, very low. And these are just all the congeners that are detected by this EPA method. So let's talk about our specification and what it said and what it didn't say, and why we might want to look at some other factors now that we understand something about hazard and exposure. Well, in California develops limits, safe harbor levels for foods to protect consumers from undue exposure to contaminants. And in California, the safe harbor level for PCBs is 90 nanograms per day. This is on the basis of studies that look at carcinogenic risk. They did not establish a safe level looking at reproductive risk. And you saw from that laundry list before that there's a lot of different toxicities manifested by PCBs. And so the issue came up, well, okay, if I'm down there and I've complied with that and I've protected myself against cancer, did I protect myself against everything else? The snake can't get me, but could the tarantula go underneath the glass and get me? And that's a good question. So how do we answer that? Well, no significant risk levels, which are based on cancer, these are generated in very different ways because, as you know, cancer is, although there's scientific controversy, it's still regulated and levels are generated with the understanding or the thought that this is not an endpoint for which we can establish a threshold. So we look at risks in a very different way, and we look at levels of exposure that we anticipate are not going to increase the population risk by more than 1 in 100,000 or 1 million or a certain number of people. And there are regulatory limits to excess, what we consider to be acceptable excess cancer risk due to a lifetime exposure. Reproductive risk is a thresholdable process. So there's a threshold below which we do not have a risk of that event occurring. And these are called MADLs, maximum allowable dose levels. And we take those from studies where we look at no effect levels and we apply appropriate safety factors. So they're generated in different ways, but both protective of these endpoints. As I said before, the risk level is a de minimis lifetime risk and the defaults of 10 to the minus 4, or minus 5, or minus 6. And we use what we call a cancer risk slope factor. And California EPA used the one that was generated by US EPA many, many years ago. And it's a risk slope factor is basically an upper bound estimate of the potency. It's used to calculate risk from exposure to carcinogens by relating the estimate of the lifetime average chemical intake to the incremental risk of individual developing cancer over a lifetime. So and I lied, I said there was only going to be one mathematical equation. That kind of is. So we take the body weight, divide it by the cancer risk slope factor, multiply it by our risk level, and we come out with our NISRL. US EPA does the same thing. They have actually modified that cancer risk slope factor that you saw. We used a 7.7 there. California used 7.7. That was one developed by EPA back in 1988. They have subsequently provided different cancer risk slope factors with guidance on different types of exposures to which that factor applies. And the upper bounds are much lower than the one used by California EPA. As a matter of fact, the one that US EPA uses that they apply to food chain exposures from congeners that are classified as high risk and persistence is 2, not 7.7. So California EPA's number is much, much more conservative than this number would be. Well, what does the 90 nanogram per day intake mean? It means that if we consumed 1 gram of fish oil a day and we wanted to take in less than this 90 nanograms per day of PCBs, we'd have to have below 90 ppb in the fish oil. If we were going to take in more, we'd have to have less. Well, there's a lot of different levels of intake of PCBs that are out there, different exposures that can occur via other different routes. And I point this out just to show you that there's not consensus, as we've heard today, there's not consensus about what this level should be, what the toxicity really is, how to calculate it, and how should we really, what level should this be to protect the consumer? For example, California sets the public health goal for carcinogenic effects of PCBs via drinking water at 0.09 micrograms per liter. That's 180 nanograms per day, not nanograms per day, not 90 nanograms per day, 180 nanograms per day. For water, they've also, although a MATL was not developed for Prop 65 purposes, there is a public health protective concentration for non-carcinogenic effects developed by California EPA for water. This includes reproductive effects, and this is set at 0.3 micrograms per liter. And the conclusion was that the public health goal for carcinogenic effects is protective of non-carcinogenic endpoints. So if I had a level of contamination that protected me against cancer, it should also protect me against reproductive risks, because that occurs at a higher level. So there's a lot of different levels out there of exposure for the consumer via different calculations, different routes, different methods of assessment. US EPA has a maximum contaminant level for water, and this is analytically based. It's based on a practical quantitation limit. Because as we talked about before, there are practical limits for analytical evaluation of our sources. So practical quantitation limit here is 0.5 micrograms per liter. 2 liters of water per day, that's 1 microgram. California Department of Health Services also adopted a maximum contaminant level at this same level. There's a lot of other regulatory limits for PCBs, and FDA has limits for PCBs in foods, EPA for drinking water and streams, OSHA has inhalation exposure guidances, and Cal EPA has drinking water levels and NISRLs. And you can see there are many different levels. There isn't a consistency or standardization among agencies or among different routes. And so if we look at even just fish oils, just looking at different bodies, US, California EPA, 90 nanograms per day. Health Canada from fish oils, we have 7 micrograms per day. Well, I just want to look at, here was the source of all the angst. These were the test results from the Proposition 65 lawsuit. And when we looked at this, 3 of these 10 fish oil supplement products contained PCBs that were in excess of this safe harbor limit of 90 nanograms per day. And that was established for carcinogenicity. But we can also look at this from another perspective, and remember I told you about the toxicity equivalent factors and TEQs. If we look at the toxicity based on dioxin-like activity, these test results look very different, because the toxicity of the PCBs is related not only to how much is in there, but how toxic are they, and they're all very different. And we really have to think about all the congeners that are in there and how toxic are they really compared to our reference. So if we look at this, we have a very different picture. And we don't have a toxicity equivalent limit that was set by Cal EPA or EPA, but we can use one that was set by the EU for a tolerable daily intake level, and that's 2 picograms of WHO TEQ equivalents per kilogram per day. And on a body weight basis, if we use a very, very stringent determination of what a health-based standard should be, we should be at 140 picograms TEQ per day. The largest exposure there was 12. It's way below 140. So what is an appropriate specification? And we can look at many different agencies, we can look at many different scientific bodies, many different countries around the world. We can look at whether they used carcinogenic endpoints, non-carcinogenic endpoints. We have different ways of looking at it. We have different standards. We have different specifications. And standardization is going to be very critical because really, what should it be? And it should be based on protection of health. And we should be protecting not only against the cobra, but against the tarantula, and we can let the bunny through. And if you look at the Prop 65 lawsuit level, we're looking at less than 12 picograms of TEQ equivalents per day, and we look at some of the other regulatory and scientific evaluations of where those intakes should be or could be that are protective of human health, we see that this is much lower than those limits. And even if we look at the absolute levels per day, even though we have California Prop 65 levels, they are also much lower than other standards set. And if we look at other standards that have been evaluated, they did assess reproductive endpoints, other endpoints beside cancer endpoints. So there is data out there, there is information, and there's a way to get at the hazard, there's a way to get at the exposure, there's a way to get at the risk. We don't have to default to a hazard-based approach. And just as a point of reference, we pulled out GRESS notifications for fish oils. These are ones used in food products, and looked at PCB specifications and dioxin-furan specifications that were present for those products. And some of these are intended for use in infant formulas, very sensitive subpopulation. And if we look at the intake of the PCBs and the dioxins and furans from those specifications of those oils, we can see where those are. And we have levels ranging from 2.4 picograms of equivalents per day down to, based only on Arachlor 1254, which is a specific combination of PCBs, 0.08 picograms, up to 30 picograms. And so specifications, even these food ingredients, differ depending upon who the petitioner was, where it was set, and many times driven a lot by the analytical capability that was present at the time that these were set. And so in conclusion, the precautionary principle is not necessary. There is a way to get at a risk-based approach to set a specification, a health-based specification for any impurity. And we use PCBs here as an example, but each one of the specifications needs to be set in this way. We need to understand the hazard. We need to marry that with the exposure, and we need to define the risk. And that way, the specification set is protective of an appropriate food-grade product that helps assure us that there are no toxicities that have not been considered, and it's protective of the cobra and the tarantula and anything else that we might have put behind the glass. And that's it. Thank you.